We're going to jump into day 2 of probability for this unit. So a quick little recap. Um, I'm going to look at example C really quick. This right here is what we would call a probability distribution, and it displays just one single event. We've got number of single preferences, and then we have the possible outcomes, which was all 4, 3, 2, 1, or none, and then their probabilities. And of course, these probabilities had to have a sum of 1 because they were all possible outcomes. Okay, so this is a way to display just a single event. Okay, but if we flip over to, I believe it's example E in our outline, you're going to see a similar display, and we're looking at lunch orders, okay, for ordering takeout. And instead of just being a single event happening, we're actually recording 2 separate events. We're looking at the type of food itself that was ordered, and we're looking at maybe like the type of restaurant that was ordered from. And so when we set up this table, it's called a two-way table, and one of the events goes on the rows and one of the events goes on the columns. Okay, we use these two-way tables a whole lot in lots of different ways in AP Stats, but one of the most common ways is to use them to calculate probabilities. Okay, I'm going to point out a couple things about how the two-way table is set up, and then we'll dive into answering all 11 of these probability questions. So the way that this probability table or this two-way table is set up is that each cell in the two-way table just displays counts. So number of meals, if you will, in this one. Okay. Sometimes probability distributions or two-way tables are already converted into probabilities. So instead of being 19, this cell would be 19 out of the grand total 225, and it would be converted most likely to a decimal. Okay. I just said this, but this two-way table actually does display the totals. That's not always the case. Sometimes you have to find the column totals and the row totals as well as the grand total on your own. So just be aware that sometimes they're there, sometimes they're not. And of course, if this was a two-way table with probabilities instead of counts, this grand total would always be 1. Okay. I'm going to go ahead and label that as our grand total. And we're going to dive into some probabilities. I'm going to go pretty quickly. Some of these are very self-explanatory, so hopefully you'll kind of catch on pretty quickly. Notice all of them start with what is the probability, which means that all of my answers will start with probability of, and then our desired outcome. Like number 1 says, what is the probability Jose will want chicken? We're going to write probability of chicken. And so on my two-way table, I'm going to look for the outcome chicken, and the probability that he would want chicken is 86 out of 225. As a reminder, you're not expected to simplify fractions. In fact, it's going to make your life easier if you don't. The one thing that you could do if you really wanted to is you could go ahead and convert that to a decimal. The only time I would say that you need to do that is if you're answering a multiple choice question and your answer choices are all in decimal format. Okay. So then number 2, the probability Jose will want Indian food. I'm going to write probability of Indian. I'm going to find the outcome Indian. It's 48 out of 225. Okay. Same idea on number 3. What is the probability Jose will want Mideastern food? I'm going to find Mideastern. The probability here is 52 out of 225. Okay. And the last one that's like this, number 4, the probability he will want vegetarian food. Probability of vegetarian is the veggie row total 62 out of 225. Okay. All right. The next couple are going to give us some wording that we need to kind of unpack. It says, what is the probability Jose will want Mideastern vegetarian? That means that I need to meet both of these criteria, or what we previously called, and we're still going to call, this is an and probability, Mideastern and vegetarian, because I want both of those outcomes to be met. Okay. But I'm going to introduce you to some new notation today. Yesterday, when we started learning probability, or last class, I should say, we just wrote out the word and. But from now on, we're going to use a very special symbol to denote and. And that is, I'm going to write Mideastern. And then for the word and, we're going to use the math symbol. It's called an intersection symbol. It looks like an arc. Okay. Mideastern and vegetarian. Okay. And last class, we talked about how for and probabilities, we're allowed to multiply if and only if we know that the outcomes are independent, or the events are independent from each other. In this scenario, I am not told anything up here that would indicate that the type of food and the type of restaurant are independent from each other. So I don't know that they're independent. I'm not allowed to multiply. But thankfully, our table very, very clearly displays for us the number of meals that meet the criteria Mideastern and vegetarian if we just look for where those two outcomes intersect. The number of meals that are vegetarian and Mideastern is 11 out of 225. Okay. All right. Same idea on number 6. What is the probability Jose will want Indian food that's chicken? In other words, we are looking for a meal that meets both the criteria Indian and chicken. Okay. So Indian and chicken intersect at the value 20 out of all 225 meals. All right. Okay, number 7. What is the probability that Jose will want Mideastern or vegetarian? Okay. When we say or, we are saying that we don't have to meet both criteria at the same time. We just need to meet one or the other. Okay. So when we say Mideastern or vegetarian, that's saying I really want all the Mideastern options and all the vegetarian options. Okay. We looked at a few ors last class as well. And we talked about how when we do Mideastern or vegetarian, we add. Okay. So I'm going to show you this with highlighters because I think it illustrates how or formulas work really well. So I'm going to go to all of the Mideastern options and I'm going to highlight that column, which is a total of 52. Okay. And then I'm going to go to my vegetarian row and I'm going to highlight the whole row, which has a total of 62. Okay. And so initially we might think, oh, we're going to add 52 out of 225 plus 62 out of 225. But if we pause for a second, we take a little bit closer look, I'm going to notice that my highlighting for Mideastern and my highlighting for vegetarian double highlighted 11. In other words, we've double counted the meals that met the criteria of Mideastern and vegetarian. So I can't just add the two totals together because that's double counting the 11. So after we add them, we go back and subtract what we double counted, which was 11 out of 225. And so if we add 52 plus 62, I'm grabbing my calculator, 52 plus 62 minus 11, we get 103 And of course, we have that common denominator already because we didn't simplify our fraction, so it's 103 out of 225. Okay. We're going to do another or in number 8. What is the probability that Jose will want Indian food or chicken? So we're writing probability of Indian. Oh, and I don't think I pointed this out. The or symbol is this U. It looks like a U. It's called a union. Okay. And that's the symbol that we're going to use for ors. Okay. So Indian or chicken. We are going to add the total for the Indian column, 48 out of 225, plus the total for the chicken row, which is 86 out of 225. But we want to be aware that when we add 48 and 86, we're double counting where those two outcomes intersected, Indian and chicken, at 20 out of 225. So we're going to subtract that so we don't double count it. Okay, and then we're going to just add 48 plus 86 minus 20, and we get a probability of 114 out of 225. All right. Okay, 3 more here. It says, what is the probability that Jose will want Mideastern given that he wants vegetarian? Okay. This wording here, we need to really understand what it's saying. It's saying we want to know the probability that he wants Mideastern given that he wants vegetarian. In other words, we already know that he wants vegetarian. That's a given, okay? In other words, this is what we call conditional probability, where I'm looking for one characteristic, but I already know a condition that has to be true. In this case, he has to have vegetarian food. What is the probability that it's Mideastern? Okay, so let me show you how we write it, and then we'll go look at the table for how do we actually find it. So we're going to do probability, and then we're going to first state the outcome that we're looking for. So we're looking for Mideastern. And then we're going to draw a vertical line. That stands for like given or conditional. Okay, so this is Mideastern given the condition that we already know it has to be vegetarian. So we write our conditional outcome after the vertical line. Okay, so on the table, what this essentially does is it narrows down our possible outcomes. We no longer are looking at all of the meals. We really now only care about the vegetarian meals because that's a given. That has to be true. So I can ignore everything on my table. This is not going very well, except for the vegetarian row. So that means that I'm using no longer the grand total of 225, I'm using the total of 62. And then out of those 62, I'm looking for the outcome Mideastern. So my conditional probability is 11 out of 62. Another way to think about that, and one that we're going to reference commonly, is that when I do conditional probability, I look where these two things intersect, Mideastern and vegetarian at 11, and I put it over the conditional total, over the vegetarian total. So 11 out of 62, intersection over conditional total. Conditional probabilities, this is very important. Conditional probabilities are the only probabilities that do not use the grand total as the denominator. Okay? There's 2 more conditional probabilities. We're going to go through them a little bit faster. What is the probability Jose will want Indian food given that he wants chicken? So I'm going to write probability of, what am I looking for? Indian, given that we want chicken. Okay, so I know that it has to be chicken, which means that my total has to be 86. And out of those 86, 20 of them are Indian food. So that's 20 out of 86. And then number 11, what is the probability Jose will want chicken given that he wants Indian food? Sounds kind of similar to number 10, so let's kind of make sure that we see the difference. Now we're looking for the probability that he wants chicken. So that goes first, and I'm given that it has to be Indian food. So if I'm given that it has to be Indian food, then I'm using the total 48. And out of those 48, 20 of them are chicken. So my probability there is 20 out of 48. You'll notice that the numerator stayed the same because Indian and chicken, chicken and Indian, they intersect at the same spot regardless of which one is listed first. What changed was the denominator because the given or the conditional total changed from the chicken total to the Indian total. Okay. All right. There is another two-way table example on the next page. And it is very, very similar to the one that we just did. Of course, it's a new situation. We're looking at customer loyalty and where the customer is located, but a lot of very similar questions. I want you to pause the video and go through and answer all 9 of these questions on your own, and then come back and check them in just a second. Okay. And I'm going to go ahead and answer all of them. And the answers are going to appear in like just a second. Okay, so here are all the answers to all 9 questions for this scenario. I do want to point out on number 6 here that the phrasing is a little different, but it still indicated a conditional probability. Didn't use the word given, it used the word knowing, but that still implied that there was a condition that we knew or that was given that had to be true. And then we were looking for another. So we were looking for 10 to 14 years, and we knew for sure that the customer was from the South. So we write 10 to 14 years given South. Okay. Conditional probabilities don't always have the word given in the phrasing. It would be nice if they did, but sometimes they'll use the word knowing. Sometimes it'll even just be the word if. What's the probability the customer's been loyal for 10 to 14 years if the customer is from the South? That would be conditional, the same way that it is in number 6. Okay, and then the bottom 2 I want to point out. Maybe I should leave the table up here so we can look at that. East or south here. Usually when we do ors, we add the total for both outcomes. So the total for east, the total for south, and then we subtract the intersection that got double counted. But if we consider our table up here, east and south never intersect, so there was nothing to subtract. So we were able to just simply add their 2 probabilities together. And then that kind of leads us to understand why number 9 is the way it is. East and south never intersected, so the probability that someone is from the east and the south is 0. Okay, there's a name for this when events don't occur, or I should say when outcomes don't occur at the same time. That is called mutually exclusive. And occasionally we use the synonym disjoint. Those mean the exact same thing, but mutually exclusive or disjoint is just when outcomes cannot occur at the same time. The probability of the and is 0, and the probability of the or is just the 2 totals added together. Okay. Okay, so we're going to go through letters G and H. Both of them have you use formulas that you've been using up here, just without a two-way table. So I'm going to go through G, and then I'll post H as well. So for letter G, it says, suppose 60% of all customers of a large insurance agency have automobile policies with the agency. When I read probabilities in a paragraph form, I always like to kind of note them as I go so that I make sure I know what I'm looking at. So this 60% was the probability that someone has an auto policy. So I'm going to write probability of auto. And then I'm always going to write my probabilities as decimals because math with percentages gets weird. Okay, so always convert them to decimals. And then it says 40% have homeowners policies. So I'm going to write probability of home is 0.4. And then it says 25% have both types of policies. In probability notation, that would mean probability of auto and home. So I'm going to write probability of auto and home equals 0.25. And then it says if a customer is randomly selected, so this is saying out of everybody, what is the probability that he or she has an automobile policy or a homeowner's policy? Well, we know how to do ORs. Probability of auto or home. Think about our formula here. It's total for auto, which we know, 0.6, plus total for home, we also know that, 0.4, minus what we've double counted, the intersection, or in other words, the and of 0.25. So this is 1 minus 0.25 is 0.75. Okay, try letter H. I'll put the answer here in just a second. So go ahead and pause while you try letter H. Okay, so same idea on letter H. We had the total for both outcomes and we had the joint probability, the and probability given to us. So to find the or, we just add the two totals, subtract the intersection. Okay, I'm going to do one more example today. I'm skipping over letter I for right now, and I want us to look at letter J. Jack and Jill have finished conducting taste tests with 100 adults from their neighborhood. They found that 60 of them correctly identified the tap water. And so we have data displayed below. This is a little two-way table, very nice and small. We have two outcomes, correctly identifying tap water, either yes, they did or no, they didn't. And then the male and female and the totals, and our grand total down here in the bottom corner. Okay, this is a nice two-way table. It would be very easy for us to use it to calculate various probabilities, ands and ors and conditionals. We've been doing that lots today, okay? But instead of being asked for a probability, we are asked, is the event that a participant is male and the event that he correctly identified tap water independent? So at this point, we're being asked to prove independence. On our first day of probability, we talked about independence a little bit and how it's super, super important. But then all of the examples that we did went ahead and just told us that our events were independent, which was really nice, okay? But it's not always the case. Sometimes we have to be able to check if things are independent. And so there's a little test that we run, our independence check. And this you have to be able to do. You get asked a lot of questions about independence on your AP test, on various on tests and quizzes, and it's a very important concept, is to be able to know if things are independent from each other. And so the easiest way to do that is to say, is the probability of A equal to the probability of A given B? So I'm going to put a little question mark over our equal sign here because we're not sure if those two things are going to be equal. If they are equal, then yes, A is independent from B. And if they're not equal, then that means that they're not independent, okay? Or they're dependent. So let's first unpack why this math works. Why does this formula prove that things are independent? So if we think about what these probabilities calculate, it will help us see why the formula works. This probability of A is just finding the likelihood that A occurs, okay? In general, total probability that A will happen. This probability of A given B is finding the probability that A occurs when we already know that B has happened, when it's given that B occurred. So if these two probabilities are the same, then what we're saying is that the chance of A occurring stayed the same even when we knew B happened. In other words, B occurring didn't alter the probability of A. Okay? So that would prove that they were independent from each other. They didn't affect each other. So the first thing that we need to do in our scenario is pick an outcome to be A and an outcome to be B. And it does not matter which outcome you pick to be A and which one you pick to be B, because if they're independent one way, they're going to be independent the other way. So when I look at my question here, it says, is the event that a participant is male and the event that he correctly identified tap water independent? So it looks like our two outcomes that we're looking at here are male and correctly identified tap water. So maybe I'll use male as A and I'll use correctly identified tap water as B. So I'm going to set up my probabilities in the context of this scenario. We're going to do the probability of male. And we're going to see, is that equal to the probability of male given correctly identified tap water? It's kind of a mouthful. I'm going to go look at how we did it on the chart here. Here's identified tap water. If they got it correct, they just labeled that as a yes. So I'm going to say male given yes. Okay, so looking at my table, the probability of male is 35 out of the 100 participants. And we're going to see, I'm going to put a question mark here again because we're not sure at this point, if 35 out of 100 is equal to probability of male given yes. So if it's given yes, then I only care about the yes column, which means I'm using the total 60. And out of those 60, 21 of them are male. So this probability is 21 out of 60. And at first glance, the fractions aren't the exact same fractions, but that's not really what I'm worried about. I'm worried about if numerically they're the same value. So if you type both of those fractions into your calculator, we get 0.35 is equal to 0.35. So what does that tell us? It tells us that the probability a participant was male stayed the same even when we knew that they got the answer correct. In other words, yeah, they're independent from each other. They didn't affect the probability, okay? So we're going to say, yes, they're independent since the probability of a participant being male was equal to the probability that the participant was male given yes, these outcomes are independent. All right. I'm going to go define a couple things on the front of our outline. I'll post that on Google Classroom, so make sure that you get the definitions written down as well.